All right, so today we're going to talk about non-dimensional numbers like the Biot number, the Fourier number, and then what their significance is, and how we can utilize them in order to basically get the temperature profile or the heat transfer in an object transiently. So this is not steady state. We're getting out of steady state. So this is now regarding transient um, transient heat transfer. So in case you're wondering what transient heat transfer means, is that now time is now a variable, and so we have to consider that. Okay, so let's first get into defining what the Biot number is. So Biot number, also called just Bi, is equivalent to h times the volume of the object divided by the surface area of the object divided by k. So you can already see that this is like the beginnings um, of kind of like contrasting the effects of convection versus conduction, right? You can already see that. The other number that we're worrying about is the Fourier number. So Fourier number, so that is called FO, and that's equivalent to alpha times T divided by that volume over area term squared. Okay, perfect. And then alpha is nothing but um, alpha equals K over rho Cp. Remember, K is the thermal conductivity, rho is the density, and Cp is the specific heat. Perfect. So this is the Fourier number. And now what we need to know is the basic equation of any transient heat conduction. So transient heat, the go-to equation is, let's use orange. So transient heat equation. So that's going to be this Laplacian theta. Remember, theta was our non-dimensional temperature. I can redefine it, but if you haven't seen the fin video, that's where we introduced theta as a non-dimensional um, heat variable. And then we have this, where essentially it's the temperature as a function of time. And then this tilde over the t just means it's not dimensional time. So t divided by, whatever the time frame is. Perfect. And I put t sub r because we're going to be looking at a sphere. So if we have let's say we had a sphere, right? We had a nice purple sphere. If I pan over here, we have a nice purple sphere, right? And we have kind of a convective layer over it, right? The convective boundary layer. We want to know, okay, well, what is the temperature profile within the sphere, right? Let's say the sphere is made of copper, and we have a T bulk out here. We have you know, a T infinity, and let's assume there's no heat generation. And let's say this temperature is below as well, or this temperature is of the ball is higher. So what is it going to be, across this air and the sphere? Well, the Biot number basically lets us know what is the role of conduction versus convection. So let me write that down. So it tells us convection or conduction. So which one is going to be dictating the heat transfer? We want to know which one is the limiting, which one is going slower, because that's going to be the one that's going to basically tell us what the heat transfer is looking like. Perfect. So looking at this equation, we can see that there's some extreme cases that we can look at. So let's first look at the first one, which is um, we're gonna call that extreme case. So extreme case one is when Biot number is really small, right? So let's say that it's really small, it's less than 0.1, right? What does the temperature profile look like? Well, if I looked at this, right, and I saw that the Biot number is less than really small, what that implies is that the conduction is really strong. A large denominator means that this is a small number. And so conduction is going really fast compared to convection. So the main resistance would be coming from convection rather than conduction. And so when Biot number is really small, right, we have H uh, V over A. That's much smaller than K. So convection is limiting. So now that we've identified that, we can kind of, intuit what the temperature profile might look like in that sphere. So if I was to go up here and I was to really zoom in on the sphere, let's say that I have the temperature here, right? It's coming in. It would dip, right? Because the resistance is really high across convection. But then the conduction is happening instantaneously. And so what ends up happening is this conduction is pretty like linear. It almost happens instantaneously. We have no resistance going on within that sphere. And then the resistance picks back up and continues for convection. And so that's what that would look like. So anywhere within that sphere always has the same temperature because conduction is going so fast, and this is relative to convection. And we can think about this as relativity, not relativity, but relativeness, due to the fact that this is transient. So everything depends on time. So compared to the conduction rate, right, the convection rate is happening really slow. Perfect. So now let's get into the math. So if I was to look at the math, right, let's go ahead and switch back over. So looking at the math, we have this equation, and when Biot number is really small, right, you can imagine that this basically gets minimized to, right, so this is really small. We can say it's virtually zero, and so this becomes zero, right? So the Laplacian of the theta equals zero. Let me just write what theta is real quick. So for anyone who's a little bit confused on what theta might be, let's choose purple. I like purple. And so theta was, remember, non-dimensionalized temperature, which is essentially the actual temperature function minus T infinity, all of that divided by T initial minus T infinity. Perfect. And so now we have boundary conditions and we have an initial condition. Why do we have an initial condition? Well, now that we're introducing time, we need to have a starting point, right? So we need to define our initial condition. So our initial condition, IC, is going to be the temperature at all positions at time 0 is equivalent to initial temperature, so Ti. And our BCs, which are boundary conditions, those are going to be minus K. Now we're going to use partials. So del T, del X, X equals L. This is going to be X equals R. R is going to be the maximum radius of the sphere. But essentially, we're talking about the outer edge. So H, you know what? Tell you what, we're going to keep it at L. So this would be for a slab. purely because if we were to take this in terms of spherical for the sphere, we would have to be using the spherical Laplacian, and it's a little bit more complicated. It's doable, but it's harder for the first time if you're seeing this for the first time. So this is going to be equal to the convection, which is T of LT, right? The temperature at the outer position, because convection is only happening at the outer surface of the slab or whatever that we're looking at. Here, let me, yeah, minus T infinity. Perfect. So we're basically saying that the heat flux that goes through the slab must equal the heat flux that's coming out through convection. So if I was to draw what's going on in terms of a Cartesian coordinate system, right, it would be, we have this slab, right, and then we have a convective layer across that slab, which is like this, and the temperature profile would be very similar. We would have the temperature going like this, and then decaying, and then it's constant, and then it's going out like this, right? So this is just the same thing as the sphere, but just in a slab form, since we're writing the boundary conditions in Cartesian coordinates. Perfect. And then we have another boundary condition, right? Symmetry boundary condition. We need to have two boundary conditions and one initial condition now that we have the two variables. The initial condition takes care of the starting point, but we need the two boundary conditions, and that is going to be del t, del x, at x equals 0, equals 0. So what that means is we have symmetry. We have a plane of symmetry here, and that means that the temperature here is symmetrical, and so there's actually no change in temperature because the temperature here must be the same as the temperature here. At that center of the block, we don't have any change in temperature going on. Okay, so if we apply these boundary conditions on this equation, what we end up getting is that initially theta, right? So we had theta was a function of x, right? X and time, and this is non-dimensional. So this is what theta initially was, but if we solve this, what we end up getting is the fact that theta is actually only dependent on time. If you go through all this, it's pretty simple to do the derivation, but I don't have time in this video to go through the derivation, and it's pretty much the same thing as the fin video. You just apply the boundary conditions and the initial condition to solve for the constant values after taking the two derivatives of this. And so now that we know that the temperature basically only depends on time, we can now go over and do an energy balance, right? So we have now an energy balance that we can do. Energy balance. And you might have heard at this point in heat transfer, you might have seen this this equation called mCp delta T, right? And this always has to, this basically summarizes the amount of heat that was generated or lost. And so this must equal the convective term. So this must equal H, the negative version, right? Because whatever goes in must come out and they're opposite sign. So T minus T infinity. Perfect. And so we get this, but oftentimes in chemical engineering, this will be written as ρV, right? Density times volume, which is essentially mass. So that should be a little bit more helpful. And then this will be written as dt. So to write it again, the energy balance, you'll see it as ρV Cp, the change in temperature over time, as equivalent to minus H A times T minus T infinity. And then if you have any heat generation going on, let's say the center of the slab is generating heat, you would tack that on here. So this is the equation that we're looking at now. Perfect. And so if we solve for dt, the change in temperature by change in time, we get dt. They are not the same t though. Minus HA divided by MCP t minus t infinity. And then what we can do is now we non-dimensionalize it, and we go to now d theta dt. This probably would help earlier. Minus HA over MCP or ρV, whichever one you have, theta. Perfect. Yeah. And so if we were to solve this with the boundary conditions that we have, what we get is that theta, non-dimensional time, is equivalent to e to the minus HA divided by MCP times non-dimensional time. And then we can define tau, a new variable called tau, which is equivalent to MCP divided by HA, and this basically returns back to e to the minus Biot number times Fourier number. And this is the main thing that we want. Perfect. So this is the equation that you're going to need for when the Biot number is essentially really small. And then if I was to convert this to the normal temperature one, that would be T of time is equivalent to T infinity plus Ti minus T infinity times e to the minus Biot number times Fourier number. Okay. So yeah, that pretty much covers how you can get the temperature profile when you have transient heat transfer. When you have a really small Biot number. So essentially, when you have convection resistance being way larger than conduction resistance. And now you might be asking, well, what about the opposite, right? What if conduction is really strong compared to convection? So we have an extreme case too. The Biot number is really, really large, right? So let's say that it's more than 1. In this case, you still have the initial conditions, right? So if I was to write the initial conditions, you have the initial condition of T at if we're trying to give spherical, right? Just to give you a combination of both. So earlier we did the slab conditions, and then right now I'm writing R for radius. So this would be for a sphere. Essentially, it's the same. That at time 0, we have an initial temperature, and that's throughout every single position. And so that would be our initial condition. The same thing for the boundary conditions, right? We have it would be dt, non-dimensional, it would be theta, but yeah, dr, non-dimensional radius, when that equals 0, this equals 0, this is symmetry, this is the symmetry boundary condition, and then we also have the constant heat transfer, heat flux, and so this is, this would be dr, um, R equals R, or since this is non-dimensional, this would be 1. R equals 1 is equivalent to H T R T. So this is what it would be. This would be the two boundary conditions. But now the difference is that the Biot number is really large, and so we have conduction basically taking over. Convection has no real resistance compared to conduction. And unfortunately, since these are these are we can't no longer say that theta. Remember what the first thing that we did was that we plugged in and we found that theta, right? We plugged in these boundary conditions, we found that theta, which is a function of position and time. When we plug these boundary conditions in, we were able to find that it's actually not a function of position anymore. Well, we can't do that anymore. We still, when we plug in these boundary conditions, we find that it's still a function of both of these. And the reason why we could do it before is because we got the equation that the Biot number was really small. We equaled it to 0, and we got this, right? But we can no longer do this. Now it's going to be the actual equation, which is, the Biot number, negative Biot number times PR. And so we can no longer do this. But there is a way to solve this. And so the way to solve this is to use something called Heisler charts. So Heisler charts. So these are like pre-made charts that map the Biot numbers, the Fourier numbers, according to the specific geometry, and they will allow you to basically determine like every single variable that you'll need. So these charts are going to be the way for you to do if the Biot number is really large. But if the Biot number is really small, we can do this, which is actually, the name for this is called a lumped parameter analysis. So let me write that down. Lumped parameter analysis. So when the Biot number is really small, we can do this, and when the Biot number is really large, we can do this. So I just wanted to point what you can do alternatively, instead of actually solving this. There's charts out there that look like this, where you have the Biot number times the Fourier number, and this would be the theta that we're talking about. And so you can basically like get at which time each of these are like at what time each of these positions are being found. And Heisler charts look very similar to this, but this is essentially the charts that you'll be looking at, and you can just map it over. Once you find the Biot number and the Fourier number, it's quite easy to map. But yeah, that covers basically transient heat transfer, the role of the Biot number, the Fourier number, the transient heat equation, and then the two cases when the Biot number is really small, we can do a lump parameter analysis, and then when it's really large, we can do we use Heisler charts in order to figure out what the temperature profile looks like in the object. Perfect. I'll catch you in the next one.